They look for space for future brood, food supply versus consumption, and thermal and humidity stability. They also monitor disease and parasite pressure. Every factor is a biological variable.
Why do bees build nests? It's a question with a simple but powerful scientific answer. When people think about a bee nest, they often imagine a home. Scientifically, however, a bee nest is a complete survival system designed to solve 4 life or death challenges at once. It handles reproduction, energy storage, temperature control, and protection all at the same time. First, a bee nest is not a house. It is a shared external womb. For honeybees like Apis mellifera, the nest functions as a place for the queen to lay eggs. It acts as an incubation chamber for the developing larvae, and it serves as a critical, long-term food storage unit for the entire colony. If the nest collapses, the consequences are immediate and devastating. Eggs die, larvae fail to develop, and the colony can collapse within days. In the world of the bee, no nest truly means no future. Second, bees build nests to control temperature. It's a hidden biological masterpiece. Bee larvae can only survive within a very narrow range, 34 to 35 degrees Celsius. They also require perfectly stable humidity levels to develop correctly. The nest allows them to retain precious heat during the cold, and it helps them release excess heat when the sun is too intense. Worker bees even fan their wings like living air conditioners to circulate air. They cluster together like a single living organism to protect the colony's heart. The nest is a biological climate control system powered by life itself. Third, bees never choose their nest sites randomly. It's a calculated decision. Before any construction begins, scout bees evaluate several critical factors. They look for height to avoid predators and a secure enclosure for protection. They prioritize morning sun for warmth and proximity to rich flower resources. The remarkable part is that no single leader gives the orders. The final decision emerges from collective intelligence, not from a central authority. If there is one key idea to take away, it's that bees do not build for today. They build their nests for the generations that are not yet born. The nest always matters more than the individual, and they will sacrifice everything to protect it. In our next episode, we'll explore the fascinating question: how do bees produce wax? And why is it considered one of nature's most perfect building materials? Stay tuned for the science behind the structure. I'll see you in part 2.
If Part 1 explained why bees must build nests, Part 2 asks the question that humbled scientists. Where do bees get the materials to build an entire living city? The answer is astonishing. From their own bodies. Bees don't collect wax. They transform energy into structure. In honeybees like Apis mellifera, bees consume nectar, and sugars are metabolized inside their bodies through a complex biological process. Wax glands on the abdomen release ultra-thin wax scales. It is a biological feat of engineering. Here's a shocking fact. Producing just 1 kilogram of wax requires 8 to 10 kilograms of honey. Every single cell is a massive energy investment. Bees build not because it's easy, but because survival demands it. From soft wax scales to precision architecture, how do they turn scales into a city? The process begins when those wax scales are secreted from the glands. Bees then chew these scales to soften the wax, making it pliable for construction. They mix the wax with specific enzymes and saliva to give it the perfect consistency. Then, they carefully attach it to the growing structure, one tiny piece at a time. What's truly remarkable? No blueprint exists. No construction leader commands the workers. Each bee contributes only a tiny action, yet thousands of microactions create a unified, flawless structure. Why are honeycombs always hexagonal? This isn't just luck, it's evolutionary perfection. Hexagons store the maximum volume of honey while using the least amount of material. They distribute force evenly, making the structure extremely strong despite its lightness. Humans call this the honeycomb problem, a mathematical challenge solved by nature millions of years ago. Bees don't know math. Evolution does the math for them, perfected over eons. Wax is not just a wall, it's a living system. It has properties that are vital for the colony. Beeswax is naturally antimicrobial, protecting the hive from harmful microbes. It provides excellent thermal insulation, keeping the nest at a stable temperature. It's flexible when warm and rigid when cool. This ensures the nest stays stable even when suspended. This means each cell is a nursery, a pantry, and a fortress all at once. Larvae are safe, and honey is preserved. Bees quietly teach us something profound. The strongest systems are not built from stronger materials, but from precise coordination and silent sacrifice. No single bee can build a nest, but together they create wonders that withstand the test of time. Collective action is their greatest strength. It is the silent engine of their survival. In Part 3, we'll push the science further. How does a bee nest breathe? How do bees regulate heat, humidity, and airflow to keep the entire colony alive? Join us next time as we dive deeper into the hidden world of the hive. See you in Part 3.
If Part 2 amazed you with building materials, Part 3 goes deeper. A bee nest is not static. It breathes and self-regulates like a living organism. For honeybees, the colony functions as a single superorganism. This collective intelligence is what allows the nest to survive. Think of the nest as a biological lawn. Inside, tens of thousands of bees and larvae are constantly consuming oxygen and producing heat. Thousands of larvae breathe, moisture evaporates from honey, and CO2 builds up. Without ventilation, the environment becomes toxic. Without a way to breathe, mold grows, larvae die, and the colony's precious honey reserves begin to ferment. Bees solve this not with fixed vents like we build in our homes, but with adaptive, collective behavior that responds to the environment. This is wing fanning, air conditioning without electricity. When temperatures rise, the workers snap into action. Worker bees line up at the entrance, face inward, and fan their wings together. It is a massive, coordinated effort. This creates a powerful one-way airflow. Hot air and CO2 are pushed out of the hive, while fresh, cool air is drawn in from the outside. Remarkably, no commands are given. The timing self-adjusts and synchronization emerges naturally through local interactions. This is self-organization, a principle now being studied by architects to design the sustainable buildings of our future. But breathing is also about heat. In winter, cold weather turns the nest into a living heater. Bees do not hibernate. Instead, they form a living cluster. They become a single, pulsing heater for the queen and the brood. The outer bees insulate the group, while the inner bees vibrate their massive chest muscles to generate pure thermal energy. They rotate positions constantly. No individual stays warm all day, but through this rotation, the colony thrives. The result is incredible. The core temperature stays near 35 degrees Celsius. The larvae survive, and the queen remains protected. Then there is humidity, the silent threat. Too humid, and fungi grow. Too dry, and the eggs simply fail to hatch. Bees regulate humidity by controlled fanning and adjusting their own density. They are living sensors, responding to every microchange. They achieve stable humidity without a single machine or sensor. It is a masterpiece of biological precision. Modern biology recognizes that the nest isn't just where they live. The nest is part of the colony's body. It is an extended body. Damage the nest, and the colony reacts like a wounded organism. It feels and responds as one. The nest teaches us that sustainability comes from knowing when to retain heat, when to release pressure, and when to yield space. Join us for Part 4, where we explore the final evolutionary lesson for humans. Don't miss the conclusion.
After understanding why bees build nests, what they're made of, and how nests breathe, we reach the final and most mature question. When does a colony stay? And when does it leave everything behind? The answer lies in survival science, not emotion. Bees are not attached to nests. They are attached to viability. In honeybees like Apis mellifera, a nest is never permanent property. Colonies constantly assess the environment. They look for space for future brood, food supply versus consumption, and thermal and humidity stability. They also monitor disease and parasite pressure. Every factor is a biological variable. When a nest no longer supports the future, bees don't endlessly repair it. They leave. Swarming, a ruthless but necessary biological decision. When a nest becomes overcrowded, egg-laying accelerates and heat and CO2 levels rise. Collapse risk increases. Nature's solution is swarming. The mechanism is precise. A new queen is raised, and the old queen departs with half the workers. The new colony searches for a better site, a clean slate for survival. This is not loss. It is life replicating itself. Bees may fully abandon a nest when parasites overwhelm the colony or fungal infections spread. Even chronic human disturbance can trigger this response. They value safety over structure. What's striking is that bees feel no nostalgia. They don't cling to past investment. Bees do not fall into the sunk cost trap, a common human mistake. Scientific climax. Bees build not to keep, but to leave when needed. It sounds paradoxical, yet true. Nests are built strong, but never meant to bind a colony forever. Because in evolution, the ability to leave at the right moment is as important as the ability to build. Biology defines a bee colony as a superorganism. Individuals are like cells. The nest represents extended organs, and decisions are survival reflexes. The system restructures itself. Nature leaves us with an uncomfortable truth. Not everything you build deserves to be kept forever. Not all persistence is wisdom. Sometimes evolution favors those who know when to walk away.